In the last class, we have covered certain topics on thermodynamics, right? So what we have done, we have seen some definitions. Let me just revise those things. We have seen system, surrounding, system boundary. Then we have seen that there are three different types of system: open system, closed system, and isolated system. Right? So we have taken around 4 examples, and we have seen whether they are open, closed, or isolated. Then I have explained you some concept on state and state properties and their classification. So you can classify a state property as intensive property or extensive property. All right. So whenever you define a state, it is defined numerically or quantitatively. It is defined with a state property. Now, based on whether it is dependent on the quantity or independent of quantity, you will say it has intensive property or intrinsic, right? Another option, another classification is extensive property or extrinsic property. It is dependent upon the size of the system, whether it is independent or dependent on the size of the system. Now I have listed certain types of the some properties which can be classified as intensive or extensive, right? So you can clearly see whether it is dependent on the size or independent of the size. Each property you can compare with respect to that concept and tell whether it is intensive or extensive. Just to give an example, specific heat, it is per kg, some amount of heat is absorbed, right? It is per kg. Whether you take 10 kg or 20 kg, per 1 kg, this is the amount it is going to absorb, right? So it is dependent, it is independent of the actual size. Then we have seen the state function and path function, when how we are going to differentiate them. Remember one thing, a property, a state property which you are mentioning, if it is a state function, it cannot be a path function. A given thermodynamic property or a thermodynamic function can be classified as either state function or path function. All right, path functions, usually the thermodynamic property we come across, heat and work, and rest almost everything is a state function. All right, only two things, heat and work done, Q and W, the notation. Okay, they are the path functions. Then we came across a concept of equilibrium. I mentioned something like a difference between an equilibrium and a steady state, right? Both are different, and there is something called as driving force. What is a driving force? It's a gradient because of which the rate of the transfer, right, so or process is taking place. In the case of a steady state, the driving force is a constant, and because of that there is a steady or continuous flow, right? The rate is positive. Whereas in equilibrium, the driving force is zero. It has come to a halt, still. Okay, so there are 4 different types of equilibrium state: thermal equilibrium, mechanical equilibrium, chemical equilibrium, depending upon whether this driving force is temperature or pressure or chemical potential, right? If all 3 driving forces are zero, that means individually you will say thermal equilibrium, mechanical equilibrium, chemical equilibrium, when their corresponding driving force is zero. Now, if all these 3 are true for a given system, then you will call it as the system is under thermodynamic equilibrium. All right. So this is the superior level thermodynamic equilibrium. If a system has to attain a thermodynamic equilibrium, it has to attain 3 different equilibriums. Right. This is just a conceptual thing what we are going to learn. Remember, long back I have already informed to you that any complex problem you have, we are going to simplify, right? So when we are simplifying these idealistic situations, these concepts come into help, because it is easy to develop equations with respect to these things. Now if we go with the complex situations, it is difficult to solve such problems, right? So we'll have to simplify them. While simplifying, these concepts of equilibrium, steady state, all these things are helpful, right? Now, at this point, I had stopped the previous class. Now, let me take up a continuation of that is reversible and irreversible process. All right, let us see what it is. A reversible process is a process that can be reversed in order, right? In a particular order, some process going on, you can reverse that order to obtain the initial state of a system. On the other hand, irreversible process is a thermodynamic process that cannot be reversed. Okay, it's one way in order to obtain the initial state of a system. Means it is one directional. Here, reversible is two directional, forward and backward. You can reverse it. In irreversible process, you cannot reverse it. Okay. Now, yeah, this is yeah, this I need to correct it. Okay, this is the correction. It's not infinite change. In the previous class I made a mention of something like infinitesimal change, if you remember well. So what it means, a small change, okay, infinitesimal change occur in the system. Here it is a finite change. All right, infinitesimal change means small difference it has occurred and it is easy to restore without adding any extra energy. You can restore, you can get back to the previous step. All right, now finite change always occurs and you cannot restore it back. Now there is an equilibrium between the initial state and the final state of the system. Equilibrium exists from where it starts when it ends. Actually the process is not at all going on, it is slow, very slow. Whereas here there is no equilibrium in the system, it is just going in a forward direction. All right. Now let me just give you a simple example so that you can understand what it means. But don't take this as one standard example that you can write it in exam or somewhere. Only for you to understand this analogy I am giving you. Okay. Now imagine two people. Okay, one person going slowly, walking slowly. Second person running. Okay, first person is slowly walking, the second person is running. All right, the first person who is walking slowly, he is walking. If you call back both of them to turn, okay, while they're moving one forward direction, they have to suddenly turn. All right, now the person who is moving slowly, quickly he can turn back because he is in a slow speed. Okay, it is easy for him, without adding much energy he can just reverse, right? He can turn back and see you. Whereas the person who is running, he needs more energy compared to this person. If the speed is high, it's little difficult to turn back and check, right? So in irreversible process, it is quick and fast and forward direction, right? It's very difficult to get back to the previous direction, I mean, reverse direction. You require more energy. You can, but you require more energy, right? So the concept here of reversible and irreversible is without adding the extra energy. I don't want to add the extra energy which is required. Without adding it, can it reverse? If yes, it's reversible. If it can't, it is irreversible. All right. So that's the concept between a reversible and irreversible process. Remember, uh, yeah. So the irreversible processes are spontaneous processes. This one, irreversible processes are spontaneous, and all reversible processes are under equilibrium. All reversible processes, they exist under equilibrium condition, and irreversible processes we call them as spontaneous process. Just like rubbing your hand, right? Let me give an example of rubbing your hand. When you rub two hands, palm, heat energy is generated, right? That means the starting action is rubbing, mechanical movement of your hand. That's the starting part. The result of that is heat is generated. Okay, that's a forward direction. Let us reverse it. Now heat your hand. Reverse direction means to start from heating your hand. If I heat your hand, giving extra energy, right? I mean, that energy, if I return it, whether your hand moves mechanically, it doesn't, right? So that's the forward, only one directional process, that is irreversible process. Coming to the folding of paper, you can fold a paper, don't cut it, you just fold it into two, fold it into four, right? You can return it back to its original size and shape without cutting. You are folding it. So you fold it into 4 times. When you return it, it becomes one same paper, A4 size or whatever size of the paper. You regain it. That's, remember the two examples what I given you here are just to understand. Okay, just the conceptual. In thermodynamics, we don't come across these things. These are not thermodynamic examples. All right. So just to give you an idea, folding of paper, when you do it, you can gain the original shape of the paper. That is normal paper. Of once you unfold it. For example, another is cooking, right? Cooking cases. That means you're adding the heat. So you cannot get back to the original raw food, right? Once you cooked it. So that is one directional. Whereas condensation and evaporation, if you take it, so slow condensation if you do it, and if you add extra energy, or if it is left like that with a small addition of energies, right? So what you call it as condensation and evaporation, they remain in equilibrium condition if you leave it to that position only without touching it. Okay, you shouldn't disturb that equilibrium process. Always it will be either condensing or evaporating. How much amount condensed? Same amount of an liquid which is condensed, it gets evaporated. This happens inside the pressure cooker, right? In an autoclave or a pressure cooker, this happens, condensation and evaporation. You should keep it untouched. That's an equilibrium process. If you know something about wet steam, right? Wet steam, that is equilibrium between liquid water and water vapor. That's gaseous phase, right? So that's condensation and evaporation. That is always a reversible process. That's the thermodynamic example. Cooking is an example. Anything that you heat is a thermodynamic example. Thermo, heating, right? Anything related to the heat is thermodynamics. All right, now let's come to something called as equation of state, EOS. All right, so let us look at this. A relationship between the variables of thermodynamics, that is state properties, pressure, volume, temperature. You have to relate them. Okay, you write one equation relating pressure, volume, temperature. All these three things are state properties. Okay, such an equation is called as equation of state, EOS. The equation that defines state of the system through its state properties. P, V and T are the state properties, right? So in SI unit we can write for the ideal gas equation. So the equation of state for an ideal gas is this ideal gas equation. Now, this is true for all those gases which behave like an ideal gas. What if a gas does not behave ideally? How do I say that it does not behave ideally? Now, going by the basic concept of ideal gas equation, I had told you it has to follow two important conditions. One, intermolecular forces should be negligible. Intermolecular forces should be negligible. One. Second condition is individual molecular volume should be very small compared to the bulk volume or the total volume. Okay, the volume occupied by the whole gas should be very large compared to the volume occupied by molecules together. I gave you the example of lab where we conduct 15 students in a group or 60 students in a group. I had given an example while explaining this concept. Right? Now, if there are some gases which do not have that particular property which I mentioned, then we call that it as non-ideal gas or a real gas. So they deviate from the ideal gas behavior and they do not follow this equation. Okay. So if a gas does not follow this equation, what should we do? We should have some alternative equation, right? So for ideal gas, it's one single equation. When I go for non-ideal gas or real gas, there are very large number of equations. Only two equations I'm going to show it to you, and we are going to use it for our calculation. Remember, this is only two equation which we are using among a large set of equation. That is what I was telling you. It is always better to simplify it to a known system. It will be easy for us to do the calculation. That is why we simplify the problem using assumptions. If I assume one gas to be ideal, only one equation I have to care. Now if I say that my gas is not ideal, I have a non-ideal gas, my complexity is increased. I have very large set of equation. I do not know which equation is suitable for that non-ideal gas. I had to do a trial and error for all the options that is available to me, and I have to find out which gas equation is suitable for the gas I have. So likewise, we have one equation, van der Waals equation, right? So you would have come across this equation somewhere in chemistry or physics, chemistry possibly, right? Yeah, two things. Looks very similar to the ideal gas equation. If you look at it carefully, this equation, this particular term is P. The pressure is rewritten with one extra term here, multiplied by V, written with one extra term over here, minus B. And the right hand side is same, is equal to RT. All right. Now this A and B are called as constants. Additional term that is given, it is for that intermolecular forces. Okay, this is the correction factor given to the pressure considering the intermolecular forces, force proportional to pressure. That's it, right? And the second one, B, it is the correction factor given to the volume considering that differences in the volume of gas molecules to the actual volume occupied by the whole gaseous system. Right? Two things are violated here. For that reason, two correction factors are given. This A and B are constant. Remember one thing, the V what I have used is molar volume. Please note it. To deceive you, I can give the total number of moles, 1000 mole or 2 kilomole kind of thing I can give, and I can give the volume 5 meter cube, 10 meter cube. But before that, before you use that value in the equation, you have to convert into this. What is this? Molar volume. How do we do it? Meter cube, volume divided by number of moles. Okay, not kilomole, meter cube per mole. All right. So ensure that always your V is in this particular unit, meter cube per mole. Otherwise, you have to convert to that unit before you use it here. Even this equation. If you refer some books, okay, or any materials, you will come across one more term here. They would have written n square V minus nB is equal to nRT. Remember those n, I have cancelled it. I have taken it with the V only. Okay, do not write n, number of moles, nowhere I am getting it. All right, so because the reason is V, I am using it as molar volume. This is one place where many make mistake. That's why I'm repeatedly telling, don't use n, incorporate along with the V only, volume. Now A is given as some equation, that is 27 R square Tc square, critical temperature. For a given gas, there is something called as critical temperature, critical pressure, and critical volume. Based on the critical, which is a fixed number, a standard number for a given gas. Okay, based on that, A and B constants depend. So based on the critical conditions, if critical conditions are given, A and B calculated like this. Usually A and B are available directly for a given gas. Look at the unit, Pascal, meter per 6, mole square, meter cube per mole. You may wonder how that terms are there and how should I remember it. Okay, you may wonder how should I remember this unit. Don't worry, very simple. This whole thing should be meter cube per mole. A plus B, A minus B, anything you do, the whole thing should be meter cube per mole. Means if V is meter cube per mole, B is also meter cube per mole, right? Both should have the same unit. B is having the same unit. Now the same rule applicable here. So P and A by V square. A by V square should be having a unit of Pascal. A by V square. V square is meter power 6, meter cube per mole square. V is meter cube per mole, that square means meter power 6 per mole square, right? So A is having a unit of Pascal, meter power 6 mole square. When you divide it by V square here, that unit gets cancelled. So this entire term will have a unit of Pascal, which is same as this, right? So you need to be careful with the particular concept. Okay, another equation called as virial equation. You might not have seen this earlier. The another type of equation. It is a series equation. You might have come across something called as Taylor series, right? So similar to that, not exactly. Now you have a term called as Z. What is this? In the next slide, I will explain you with the Z. Leave it out now. PV by RT. The equation is this: PV by RT is equal to 1 plus B by V plus C by V square. I can go on doing it. Plus D by V cube plus E by V power 4. Like that, I can go on doing it. The After second order term, third order onwards, right, I will cut it. The next portion I'll neglect. Okay, so after v power 3, whatever it is there, I'll neglect it. That is called as truncation. So that is why this equation is called as truncated form of virial equation. So it is 1 plus a constant. B is a constant, not this B. This is different, this is different. Two different equations. Okay, so B by V is a molar volume, plus C is a constant by V square. Now, this B and C are called as virial constants, coefficients. B and C are called as virial coefficient. First virial coefficient, second virial coefficient. How do I say that first and second? V power 1. So that is why B is virial first order coefficient. V is power 2. So C is second virial coefficient. Right? Now, instead of V in the denominator, I can also write like this, another form of equation. Okay, it's not derived equation, it's a empirical relation. All right, so PV by RT is equal to 1 plus, similar to this, but instead of V I have P here, I have written B dash. All right, now some books refer this as B dash and this as B. Doesn't matter, numbers are different. This B and B dash, numerically they are different. Just to ensure that when I write both together, just to ensure that both are different, I am writing B and B dash here. When you write both equation together, if you write B dash here and B here, doesn't matter. All right, so their values are uniform, unique, so that you don't have to worry about that. Similar to that, C dash P square plus some more terms are there, P power 4 kind of equation terms are there, that I have cut it. That's called as truncated. Now this B dash and C dash, again they are also called as first virial coefficient and second virial coefficient. This Z is called as compressibility factor. It is a constant. PV has same unit as RT. The unit of PV is joule, joule per mole. RT has a unit of joule per mole. Both have the same unit. The unit gets cancelled. Z is dimensionless. There is no unit for Z. It's a constant. All right. So these two equations, both equations are called as virial equation. Now when you write this equation B and C or B dash or C dash, when I solve the numerical, you'll get to know, you will not be told about equation. Okay, which equation of the two you have to use, you will not be told. One side is PV by RT, on the other side it is 1 plus these terms, which you have to use based on the unit of B or B dash, C or C dash. Based on the unit, it's a number, a constant that will be given to you. Based on the unit of that, you should be able to identify which equation should be used. How do I know that? B has a unit inverse of V, right, or same as V, right? B should have a unit same as V. Why? This unit of B and unit of V should get cancelled because Z is a constant. So Z is a constant or dimensionless, no unit for Z. So B by V should not have any unit, dimensionless, right? So B should have same unit as V. C should have same unit as V square, right? So if I have some term, I mean the constants are given as in terms of meter cube per mole and meter power 6 per mole square. That means I have to use this equation. I have to use V in my equation. Now, if the constant is given in terms of a unit which is inverse of pressure, because unit of this and unit of this gets cancelled, right? So total should be unit dimensionless. So if this should be Pascal inverse. This should be Pascal power minus 2. All right. So instead of Pascal power minus 2, I can give it in a different way. That is Newton per meter square. All right. So that way also it can be given inverse of that. Right, let's see the numerical, then you will understand the concept. Now before that, let me go back to the topic on compressibility. All right, so let us define it first, what it is. So the compressibility is nothing but it's a ratio of volume occupied by a real gas to the volume occupied by an ideal gas under the same conditions of pressure and temperature. So what it is, it's a ratio. Z is a ratio. First thing, ratio means there is something in the numerator, some term in the denominator. What goes to the numerator? Volume occupied by the real gas. We are talking about a real gas here, right? Not ideal gas. So we are talking about a real gas. The volume occupied by the real gas is V, right? Then ratio to the means in the denominator in volume occupied by an ideal gas if it was under the same pressure and temperature, right? How do I find out the volume of an ideal gas? PV is equal to RT. For an ideal gas it is PV is equal to RT. I do not know the volume, so how do I calculate? V is equal to RT by P. Okay, I've written it RT by P. Remember, V is the volume occupied by the real gas. So when I rewrite it, the Z equation will be equal to PV by RT. All right. So this is how we are going to make use of compressibility factor. Now remember, compressibility factor for an ideal gas, since it is an ideal gas, right? For an ideal gas, both numerator and denominator will be same. Z will be equal to 1. Right? You can see the green bar here. This is called as compressibility factor chart. What is the advantage? Using this graph at different temperature, here it is, different pressure and different temperature. The line represents temperature. It is called as reduced pressure and reduced temperature with respect to the critical pressure, with respect to critical temperature, right? So it is a relative measure. The way we calculate your marks, right? So you would have scored 15 out of 20 in the CIE. If I have to convert it to a percentage scale, I divide it by 20 multiplied by 100, right? I convert the scale. Same way it is divided with the critical pressure, critical temperature. So it's a relative measure of reduced temperature, reduced pressure. All right. Now a chart is prepared. This is applicable for all the gases. All the gases, same graph can be reused. So at a particular case, we can identify. You just have to mention a temperature and pressure. It's reduced pressure and reduced pressure, temperature and pressure. Say reduced pressure is 2, reduced temperature is 1.2. Here it is, right? Here it is. So at this point, what is the Z value? This is around 0.6. Likewise, you can find out the Z value for a non-ideal gas. For an ideal gas, it will be 1, the green bar. All right. Now, always keep it in mind, Z can be more than 1 or less than 1 or more than 1. Okay, Z can be less than 1 or it could be more than 1. That is also possible, but not shown in the graph here. Z is not less than 0. Z is never negative. Z cannot be negative. Keep it in mind. It's always more than 0. All right, more than 0. It could be more than 1, it could be less than 1. 0 to 1 or more than 1. Not very high, not more than 2. All right, it's less than 2 actually. None of the value goes beyond 2. Okay, now let us solve some numericals based on this. Some 2 or 3 numericals are there. Quickly I'll go through it. I'll explain you how to solve the numerical based on the equations what we have seen as of now. 1 kilomole of CO2, carbon dioxide, occupies a volume 0.381 meter cube. Did you observe that it is meter cube? Absolute volume. I made a mention of 1 kilomole here, 1000 mole. 1 kilomole, it's written in word. There is no number written, it's written in word. Okay, 0.381 meter cube at 313 Kelvin. Find the pressure of CO2 using ideal gas law, van der Waals equations. 2 independent problems, okay, for which the data is same. For the same gas, assume that it follows ideal gas, what would be the pressure? Now assume that it is van der Waals equation, what is the pressure? For van der Waals equation, the units are given, I mean A and B constants are given to you directly, right? Now, molar volume, first you have to calculate. How do I calculate molar volume of the carbon dioxide? Volume 0.381 meter cube per the number of moles, 1000 mole, right? So I have to calculate in meter cube per mole, 3.81 into 10 power minus 4 meter cube per mole. Let me note on the temperature also, 313 Kelvin. Let us go for the first solution, ideal gas law. If I use ideal gas law, PV is equal to RT is the equation, right? So pressure of CO2 I do not know. So I'll retain P on one side, V I'll take it on the other side. So it becomes RT by V. I know the value of R, 8.314, temperature is 313 Kelvin, volume is molar volume. Now this is the point we need to be careful. It is the molar volume that I have to take. Okay, so whatever may be the value given to you in the numerical, you have to convert first to meter cube per mole. Now calculate it and the value is 6.83 kilopascal. It's actually 6830 pascal. I have written it in kilopascal. It's not mentioned there in the numerical, but I have put it in kilopascal. All right. Now, second thing, van der Waals equation you have to use to find out the pressure of carbon dioxide. A and B values are given to us, and I know the equation. All right, the equation, van der Waals equation, I know it. So based on the given information, I can find out now the remaining things, that is pressure. First, what I have to do is I have to substitute. Always remember, follow this method. When you are using an equation, first write what you are doing. You are using this equation to find out pressure of CO2. Then constants, whatever data is given, you can write it. Next is the equation that you're using. That's important. Write the equation carefully without any modification. Then simply substitute the value. Substitution is also a step. Don't write saying that I have a calculator, I can put it in a calculator and write. Don't do that. Okay. Substitute the values on a paper. That's the next step. After substitution, go on simplifying and find the final answer and write it. Why should you substitute? What is the necessity of substitution? Now let me take it in the examination point of view. Say that you have done this calculation directly and written an answer. All right, you have written this equation. You have written this answer 8.15 kilopascal, not 5.118. Written 8.15 kilopascal. Everything is correct. Only thing is your eyes deceived you when you wrote the answer. All right. Now there is no step written. What should I do? I should give you 0. Even though you have substituted correctly in your calculator, even though you have got the answer correctly in your calculator, that is 5.18 kilopascal, just because your eyes deceived you while writing, eyes and hands together, okay, 8.15 you are written, you will get 0. Now, what if you had substituted? You have substituted everything correct, absolutely correct. Okay, so you know how to do it. You have written, put it in the calculator, everything is fine. Only thing is last thing, okay, 8.15 written. Now, since the substitution is correct, I have to consider at least to certain fraction of your marks, maybe up to 50 or 60%. Instead of getting 0 mark out of 1, you may get 0.5, right? 50% mark you can fetch it. So that's the advantage. That is advantage 1 in terms of examination. Second thing, this may be a part of a major problem. It could be a small part of a major problem you are solving. Say that at the end, you are supposed to get some kind of result. You are expecting some kind of result at the end. You do not get it. You know that you have gone wrong somewhere. Now you have to pinpoint a location to find out that you've gone wrong. Now, if the substitution is not done, directly written the answer, it's very difficult to pinpoint whether the mistake is here or somewhere else. If you have written this step, all right, and say where is temperature, that 313, okay, instead of 313, how much it would come to? Around 50 degrees Celsius, right? 13 or 40 degrees Celsius, correct. So around 40 degrees Celsius it will come. You have written the temperature in degrees Celsius. Let me assume that you have written the value in degrees Celsius. You are supposed to write this value in Kelvin. You can now, since the substitution is there and this value when you see it, it is in degrees Celsius, but it is supposed to be in Kelvin, you know that. Now you can exactly pinpoint, here is the mistake, rectify this, rectify the whole solution, right? So that is the necessity of a substitution after an equation. Otherwise, yes, you can use a calculator and write, no problem, but there are different issues associated with that. All right, try to avoid the direct solutions. Another problem, calculate the compressibility factor and molar volume for methanol vapor at 500 Kelvin and 10 bar using the truncated virial equation. So you have to find out compressibility factor as well as molar volume for methanol vapor. Temperature given 500 Kelvin, pressure given 10 bar. Now you should know temperature is given, pressure is given. Pressure you have to put it in SI 10 per 6 Pascal. You have to use truncated virial equation. When you come across truncated virial equation, there are two equations in front of you. One, this one, V by V form, another B dash V. Two different forms are there in front of you. Which one should you use? To identify that, go for the virial coefficients given to you in the numerical. I written it here, rewritten that. Virial coefficients given. Now, when I look at this virial coefficient B, Okay, I written simply B here because I know it beforehand. It could be B or B dash, anything, you do not know. It could be B or B dash according to this equation, anything. Look at the unit. Now when you either B divided by V or B dash P, whatever you do, the unit should be, there shouldn't be any unit. Unit should get cancelled out. Alright. If B is meter cube per mole, this value is meter cube per mole, it gets cancelled over here. And the C is meter power 6 per mole square. So it gets cancelled over here. That means I have to use this equation, not this. Not the second one. I have to use the first equation. If I have to use this equation, the unit should be such that it should cancel out with pressure. It should cancel out with the pressure square, right? So that way I should have the unit. Now I'll be using this equation. How should I do it? I don't have to write Z in the beginning. Don't write Z. Only at the end you have to calculate, right? Keep it away. I substitute P, V, R, T, B by V, C by V square. All those terms I substitute. Pressure 10 power 6, V. Calculate the molar volume. I do not know. Capital V, I put it as it is. Retain it. 8.314 R. Temperature 500 Kelvin. Should be in Kelvin. B value, C value. This negative sign. Somewhere is there, no? Yes, here it is. Minus. Carefully the minus. So minus sign I put it. Okay. So I substituted the value as it is. Next, what I have to do is I have to simplify that. Okay. Before I simplify, I just show you. You can see that this equation, in this equation, you have only V as the unknown term. Only V is the unknown term here, right? So when you have one unknown term and one equation, it is easy to solve. You know that, right? So let us do that. So you have to get this simplified form. How did I get this? If you do not know how to solve an algebraic equation from there to here, let me explain you how did I get that. First, you have written this equation. You have substituted all the terms into this. Now you have to modify this. How do I modify? It is easy for me if all these unknown terms are in the numerator. They should not be there in the denominator. That is primary thing. Okay. How do I get it to the numerator? Look at the denominator. The unknown term is V, volume. Highest degree is V square. So what you do is all the terms, wherever terms you see here, term number 1, 2, 3 and 4. Each term you multiply with V square. Right? Multiplying LHS with V square, multiplying RHS with V square. V square. Okay, V power 2. Now, once you are doing it, this 10 power 6, 8.314 and 500. This thing you can calculate numerically. You can solve this, simplify this numerically, no problem. We have problem with that unknown term V, right? So multiply throughout with the V square. What will happen? First term, V into V square, V cube. There was a term, I have calculated it. That term is that 10 power 6 divided by 550 divided by 8.314, right? That one, 240.558. Okay, there was one V term, multiply by V square. There was 1 here, multiply by V square. There was denominator V was there, numerator V square, it gets cancelled, you get V. Denominator was V square, multiply by V square, you get constant. Right? Now you see the equation, unknown term V is in the numerator only. There is nothing in the denominator. Now it is easy for us to solve. Okay. Now before you solve it, rearrange the equation in this particular form. What is this form? On the one side of the equation you have 0. All the terms are on one side. And ensure that this highest order term is having a positive value. If it is having a negative value, you should have taken the other side. That's it. Okay. So ensure that this is the format. On one side you have the 0. Now this is a cubic equation, right? Cubic equation, V power 3, V square, V constant. It's a cubic equation. Now use your scientific calculator. You have a mode in that to calculate a cubic equation. I guess that all of you know how to use a scientific calculator and find out the cubic equation solution. Right now I assume that you know how to do it. All right. Now it's a cubic equation, so there should be 3 solutions for that, right? And the unit is in meter cube per mole because all in SI unit, RT and P. So you'll get unit in meter cube per mole. So you get 3 answers, 0.0044 minus 0.003, 6 into 10 power minus 5. Now the real dilemma comes into picture. What is that real dilemma? Of these three, which is the correct answer? There are three answers. Which should I take? All right. Now, let me give you some details on this. The correct answer is the first one. Not always. I am not saying that first answer is the correct one. Okay. In these three, the first answer is correct one. The second, the remaining two, I am going to reject it. They are not my answers. I am going to reject it. The reason is here. Why I have rejected, let me tell you. Volume cannot be negative. So if you have a negative value, outrightly reject it. If you have all three negative, means something wrong in your equation. Okay, if all three are negative, either something wrong in your equation, option number one. Another possibility is that your substitution in your calculator is wrong, or some problem in the problem itself could be having some trouble, negative or positive, some value, something is missing there. All right, let me assume that everything is correct here. So it's negative, I'll reject it. Then among the positive values, consider the highest positive, that is highest value. Among the positives, consider the highest value, that is the volume of vapor phase. The lower volume is the molar volume for the liquid phase. All right. So don't consider the lower volume, consider the higher volume. So I have considered the higher value. All right. So that is the molar volume. Now I have to calculate the compressibility factor. Given this volume, I have to substitute in this equation. This V, I know it, PV by RT, substitute, and I get Z is equal to 1.058. I told you that for ideal gas, Z value is 1. Right? So I have written 3 decimal order. So always Z, you write it in 3 decimal places. Yeah. Now that's the end of unit 1. Now what we have learned in this chapter, in this particular chapter, let me summarize it. We have learned quantities, system of units, unit conversion for quantities. We have seen different system of units, that is SI, MKS, FES, CGS, right? So we have seen, we know how to do the conversion among them for some quantities. We know the conversion factors also. Then we came across mole and molecule, how to convert mole to mass, right, using molecular weight. I told you that that time, mole multiplied by molecular weight gives you mass. Don't forget that equation. Now, next units, you require it badly. Next 2 units, you are going to use that again and again for all the problems, most of the problems. Mole into molecular weight, right? Then we have seen how do we convert different forms of expressing concentration. We know how for different types of the system. We have seen for the gases, we have seen for the liquids, solids, we have seen a mixture of the two, that is solids in liquid, right? Example, the different types are normality, molarity, molality. So given a situation, we know how to calculate them. We know how to calculate mole fraction or mass fraction. Interconvert between them. Given the molecular weight, you can interconvert between mole fraction and mass fraction. We know how to calculate volume fraction, pressure fractions. Given the condition, mole percent, volume percent, pressure percent, you can find out the partial pressure also. We have seen ppm and ppb, how to do the calculation, right? So under ideal gas equation, so we have used it, ideal gas equation, to calculate the different conditions of pressure, volume, temperature. We have used that to calculate average molecular weight. We have seen gas density calculation, and we know something called as STP, NTP, standard temperature pressure, normal temperature pressure. Then buffer system, there we have used Henderson-Hasselbalch equation. We have calculated pKa and different types of buffers we have seen. In thermodynamics, we have seen the real gas equation. We used van der Waals equation and virial equation. We know how to calculate the compressibility factor or calculate the volume. Okay. Same equation you can use for the pressure. Pressure is simple. You have to substitute the volume there. P you can calculate directly. What I mean is this equation. What is that? Yeah, this equation. All right. So I have not solved that problem. I have uploaded a file in a PDF file in the Moodle with some solved problems. There the numericals are there, which are not done here. Given the volume, that is easy actually. Given all these things, given volume instead of pressure, instead of 10 bar, if I give you the volume, you can substitute the volume here. Only one unknown is P here in the numerator. You can easily calculate the pressure, right? Calculate the pressure. That is the same previous problem here. Calculate the pressure using this. Instead of van der Waals, I'll give one more virial equation. Constants I'll give you. So in that case, what you will be doing? You substitute that volume, molar volume will substitute, calculate the pressure. Okay, given BC and temperature. right? So that is how you can solve it. So we have seen compressibility factor and compressibility calc, right? Okay, that's the end of unit 1.